welcome now Dr. Tim Ashworth, our very own impedance product manager, with whom many, if not all of you, had already a pleasure to interact, discuss your project, and solve some problems. Today, Tim will talk about transient acquisition using LabOne and the MFIA. Tim, are you ready?
Thank you, Magdalena. Yes, ready and very excited to be here today. Firstly, thanks to Ramon for an excellent talk there. Very interesting. Good to hear about complementary techniques to DLTS. And secondly, thank you to everybody for joining us today. This is our first DLTS user meeting. We hope it won't be the last. And from the attendance today, I'm very happy. We're actually very positively surprised at how many people joined today. So thank you very much. Today, in this tutorial, I'm going to take about 30 minutes to give a brief introduction, firstly to the company, in case anybody doesn't know us, and then secondly to the MFIA, followed by a live demonstration of a transient measurement. Of course, today we'll be at room temperature, so we're just working on the desktop with a simple LED. Nonetheless, it will give you some hints and tips on how to improve your measurement, hopefully. So let me start with a very brief introduction of the company. So we are Zurich Instruments, and our mission is to provide the best-in-class dynamic signal instruments. And I think this nicely matches the needs of the DLTS community. We want faster measurements, we want more precise, we want lower noise, and this is exactly the aim of Zurich Instruments. So how do we do this? Quite simply, if that's too small a word, we take the available hardware, so the best FPGAs we can find. We put with it a very low noise analog front end and otherwise excellent power electronics. And then onto that, we have our own firmware and software, which you know as LabOne. And this is the operating system of the MFIA, and in fact, of all of our instruments. So in addition to impedance analyzers, we offer quantum control systems and lock-in amplifiers and boxcar averages. So we have a nice portfolio of instruments. We're headquartered in Zurich. We are currently 100 people and growing fast. We have offices in China, USA, Italy, Korea, and France, and partners covering the other major markets. More importantly, we are a company of scientists run for scientists. So we understand, most of us have been in research, we understand the challenges of research, and we hope to offer application support accordingly. And some news which is just a few days old, Zurich Instruments is now a Rohde & Schwarz company. So we've been acquired by Rohde & Schwarz. It won't change how we deal with you. Zurich Instruments will continue as an independent standalone company. So let's get started with the tutorial. Okay, so today's tutorial, here's a quick overview. Firstly, I'd like to introduce the MFIA and explain a little bit how it is unique, to what extent is it unique? And then secondly, why does it suit DLTS? Then in the live demo, I'll start with an introduction of the Impedance Analyzer tab, explain a little bit about how we're measuring, how that's set up. We'll do some spectroscopy before moving to the setting up the voltage pulse. Then we'll move to the plotter module to have a look at the signals in real time. Then we'll move to the DAC module and we'll acquire with the DAC module. We'll use triggering to average transients. Then finally, we'll look at optimizing the current input range and the filter bandwidth. If we've got time, we can go to working with small signals, because I know that not everybody wants to work with 1 volt or many hundreds of millivolts. And also, thank you to the questions today. I see that there's some interest in various frequencies, so frequencies other than 1 megahertz, and I'll be happy to demonstrate that as well. And then at the end of the half hour, we can have a wrap up and hopefully some nice discussions. So what makes the MFIA unique? And I think let's start with the hardware. So it has a wide frequency range. It's 1 millihertz to 5 megahertz. So it's very flexible in the frequency range. We can handle high impedance. So if you have a low capacitance value, you can still measure that reliably. The most important for DLTS is, of course, the fast measurement speed. At 1 megahertz, the typical operating frequency, we can measure in 10 microseconds. The MFIA is based on the MFLI lock-in amplifier. So if you have the MFLI, it's one and the same in terms of hardware. You would just need the impedance analyzer option to give you the full functionality that I'm demonstrating today. Nonetheless, the MFIA retains the full lock-in capability, so you can really use your MFIA as a lock-in amplifier. And a word on the architecture. So in contrast to some other impedance analyzers, we don't use an auto balance bridge. We make a direct IV measurement, and this really allows us the ability to measure quickly. So all this, that was a little bit about the hardware. The software as well is unique in that we offer both time domain tools, such as the plotter and the DAC module, so you can measure impedance parameters as a function of time. But we also offer, of course, the frequency domain tools, such as the sweeper module. So you really have these, so adding the hardware and the software, you've got the ability to take flexible measurements, and I think, as Ramon pointed out, to do spectroscopy measurements, in addition to the DLTS, as well as capacitance versus voltage. So it's a very flexible instrument. So let's go to the next slide. Okay, I think today it's important to take a moment to explain why the MFIA is suitable for DLTS. I've already mentioned the speed. So at 1 megahertz, we can measure reliably and precisely in 10 microseconds without any waiting time. And then even if we want to measure at low frequency, so if you want to measure, for example, perovskites at 80 kilohertz, thank you to Sebastian Reichert and Carsten Giebel, then the measurement time is 90 microseconds, so still very fast. If you need to go faster than this, we can actually use gated data transfer, so you can trick the instrument to measure even faster. And I can maybe say a few words on that later on. And uniquely, we can measure the current simultaneously. So you don't need to choose between capacitance and current. You can measure both simultaneously. And if you have the MD option, you can even measure the current at a different frequency to the capacitance. So that might open up unique flavors of DLTS. The way that we stress the DUT, so how do we add these pulses? You can use the MFIA itself, and I saw a couple of questions in the chat. People interested how to do that, so I'll demonstrate that today. We can use the threshold unit and the auxiliary to form a square pulse that's configurable. But the pulse itself is added via an analog channel, so we have a direct connection to the output using the auxiliary input 1, and that means you can easily use third-party generators. And I think that's quite an important aspect to consider. And thirdly, if you want to use optical stressing, so a laser light, you could trigger that light source with the MFIA, or you can trigger the MFIA with the light source. So we have both triggers in and triggers out. And then finally, I think Ramon put it very nicely, the complementary techniques that you can work with DLTS, such as impedance spectroscopy, admittance spectroscopy, so thermal admittance spectroscopy in Ramon's case, CV measurements, fast CV, and also fast impedance spectroscopy. Fast refers really to the fact that we measure at the limit of the instrument, so on the tens of microsecond scale. Okay, so still on the topic of DLTS, I'd like to also take a moment to just to give it the more of the worldview, where else fast impedance measurements can be useful. So if you have your MFIA, maybe you have colleagues working on fast CV, as I've mentioned. So that's really the ability to ramp at 3000 volts per second and still track the capacitance. Secondly, sensor characterization. So a lot of sensor developers, they want to know the change in impedance of their sensor, but they want to know it fast. They want to know it much faster than the change of the real world to ensure that it's reliable. Haptics and wearables. This is also somewhere where you want to make sure that you can measure that impedance change very quickly. And fourthly, microfluidics. This is where typically you pass a cell through a microfluidic channel. As the cell goes through some electrodes, you measure a change in impedance, and therefore you can characterize the cell, or you can sort the cell. And that's also a very interesting application that I just thought I would let you know about where else fast impedance measurements can be used. Okay, so I think now we'll get on to the demo. As I said, today we'll be using a simple red LED. It's mounted on a carrier, so an MFITF carrier as shown in this picture here. The difference to the picture is today I'm using 3-meter long BNC cables. So I have 4 of them. And I think this is a much fairer test, because I know none of you are working without cables. So I think it's important to demonstrate this with cables. I will apply a voltage of +2 to -1 volt using the threshold unit and the auxiliary module of LabOne. And I'll demonstrate how we can do that. And then the BNC cable here, the loop back, this is to add the DC pulse to the AC test signal. And this is where you would put your third-party generator if you needed. You would simply add it at auxiliary input 1. I'm also going to take the time to look at the complementary measurements, such as impedance spectroscopy and CV measurements. So let's get started. Let's see. Okay, here we see, I'll go to full screen here. Here we see the user interface of LabOne. Just to put things into perspective, LabOne is what's running the instrument. The user interface is the web interface. But of course, I know a lot of you are using API. So my presentation today will be focused on the user interface. And my colleagues, Meng Li and Roberto Fortes, will demonstrate some API control to give you the fuller picture. So let's get started. On the top, we have an impedance analyzer tab. We have a test signal of 500 millivolts. And then in the advanced tab, we've set the measurement bandwidth quite wide open to 1 kilohertz. And more importantly, we've increased the data transfer rate to the absolute maximum, which is 107 kilosamples per second. And this corresponds to the close to 10 microsecond per sample. You can hide away the advanced tab, and then you get more of a screen here. I'm going to start with a sweep of impedance. So here I've got a sweeper set up to sweep simply the frequency from 10 kilohertz to 5 megahertz. Let's get that started. And you can see here, we're getting 2 traces here. We're getting the capacitance, 28.7 picofarad as a function of frequency, and the phase. You can see we're getting a nice, almost -90. I think this measurement here is -89.99. Gives you an idea of the phase precision of the MFIA. Now, as the frequency increases, our phase doesn't really track what we would hope. We would hope for a -90, but nonetheless, we're only at, even at 5 megahertz, we're only 1 degree off the -90, and that could be compensated by more careful fixture compensation. So now we know the capacitance of this LED. We could probably optimize this with the current input, but I think it's more important to move on to the other techniques. Now, let's stop this one And now I want to show, also using the sweeper, I want to show that you can do capacitance versus voltage. And instead of reconfiguring this sweeper, I've actually just opened up a second sweeper. And in this one, instead of sweeping the frequency, we're sweeping the offset. And now I'm going to go from -1 volt to +1 volt. We can go bidirectional, and you can see here nicely that we're getting, so here we have the capacitance, the phase, all as a function of voltage, and they're all easily available in this dual plot view. I've set it to bidirectional, so we're going to bounce back and forth. We can also, there we go, scale that a little bit better, so you can see the current going through the LED as a function of offset. And this is at a oscillator frequency of 42 kilohertz. You're free to change that. In fact, let's do that. I think it's more important that we have a look at 1 megahertz. There we go. Change that to 1 megahertz. And now we can see slightly different behavior, but nonetheless, we get a reliable measurement of capacitance here. And we can also see that the capacitance changes with offset voltage, of course, that's why we're here today. And we see that it's 25 picofarad raising up to 40 at +1. So we're going to use this same voltage pulse to precipitate a change in capacitance from 40 to 25 picofarad. So we can stop that here. We're going to take a moment to set the offset voltage to 0. Oh dear. Bad fingers, 0, there we go. And then we are going to start by producing some square pulses. And here in the threshold unit, we've configured this to output, enable and disable 2 seconds and 5 seconds. We then feed this into the auxiliary tab where we can scale the output. And we've put the output onto auxiliary output 1, which we then feed back into auxiliary input 1. So it's quite a simple process. If anybody has trouble, I can share a settings file that will get you up and running, no problem. There's also various blogs on this. So now let's have a look at that. And we can see now, if we start the plotter running, now we have, this is a live measurement of the auxiliary input. And you can see it's changing from +1 volt to -0.5 volt. And then we can simply have a look at the capacitance. Oh dear, I see that I haven't added at the moment, this voltage is not being added to the AC test signal. So this is a common question we get. And then you need to go to the lock-in tab. And in the lock-in tab, you can click here, which is add, and the tooltip tells you exactly what it does. It adds the voltage that it sees at input 1 to the AC output. So we click there, maybe you heard the relay. Now we go back to the plotter, and we can see now that we're nicely getting a change in capacitance, which corresponds to the slow measurement. So you can see we're going from, maybe I stop that and put some markers. You can see that we've got 40.7 going down to 25. Let's zoom in, have a look at this, see how sharp it is. So I can zoom in with the mouse, the track wheel. Let's have a look here. And what I want to demonstrate here is how quickly we're able to resolve these changes. And I think that for DLTS is very important. So let's expand that a bit more. Okay, I think that's, we can now put the one cursor at the top and one at the bottom, and you can see now that delta in time is 10 microseconds. So that gives you an idea of the time scale that you can measure changes in capacitance or other impedance parameters, by the way. We're not limited to capacitance here. All right. So now we've got the transient speed, demonstrated the transient speed. But of course, the plotter, it doesn't give you the opportunity to trigger and acquire a fixed number of transients. So we're going to use the data acquisition module. There we go. Here's one I made earlier. Let's take a single shot. There we go. And what I will show you first is we're going to take a single shot rather than averaging. There. And the advantage of the DAC unit, it is triggerable. So for example, here in the settings, we're using DMOD1 trigger out, and we're saying, please acquire when you see a positive edge. And what's more, we've added a delay. So please acquire 1 millisecond before the positive edge. And this is the wonder of digital buffering. We can measure before the triggering event. So that's quite a nice feature. So that's minus 1 millisecond. You can, in the grid, you can specify how many points you want to measure. So if we just measure 512, take a single, you can see we just get one transient there. You might be interested, so in measuring 2000, there we go. The good thing is this trigger is digital, and it means that we can really get a nice sharp edge, which allows us to average out the transients. Now, to show a noisy transient, what I think we'll do is we'll go to the plotter and start this running. And then firstly, I'll reduce the test signal to 10 milli to give us a little bit of a challenging measurement situation. It's too easy if we have nice clean signals. We want to really push things to the limit. And you can already see now that with such a small test signal at the end of 3-meter cables, it's looking pretty noisy, but still measurable. So let's now reduce the voltage, the difference between capacitance 1 and capacitance 2. So we can scale that by, let's say, by a factor of 10. Might regret this. Let's see how it looks. Here we go. So now we have a very small input. We can hardly see the change in capacitance. So what I'm going to do now is optimize the measurement. So first I go to the lock-in tab, have a look at the current input, and we can see here that we have a current input of 10 milli. This is the white bar, and the gray bar represents the total signal. It's very small. So what I'm going to do is reduce that to 100 micro. And I think this will already give us a much better signal. So you can see already we've optimized the current input, and we can easily see these small changes. So now let's have a look in the data acquisition tab. So that was with the big signals. Now with the small signals, it's looking pretty noisy. Still easy to see, but nonetheless. Now I want to show you the magic of averaging. Of course, it's not magic. It's pretty easy. What is very nice to do though is to use the digital trigger. So digital trigger 1. So I'm feeding the square pulse. I'm feeding it in the DIO tab. I'm feeding it directly into the trigger out. And this makes for a very nice measurement. And in the grid, we can now change repetitions. Instead of 1, we change it to, let's say, 20. And now when we trigger, when we press single, we will see it will average 20 different transients. And you can see nicely that the noise is now significantly reduced. I mean, yeah, you could do that in post-processing, but the MFIA does that on the instrument itself. So now you have an average of 20 transients. Let's go even, let's push it a bit further. Go another, I don't know. Let's go to another factor of, okay, factor of 10. Let's do a, see if we can still get that now. So you can see with, there we go. That's nice. So with just 1, I think we can repeat that with just 1. Basically, you can't distinguish the two states. But once again, with the DIO, triggering, we do a 20 average, and suddenly you can really, you can pull that information out. And now let's have a look at, let's zoom it in here, add some cursors. So we can put cursor 1 here, cursor 1, 2 there. So just with this simple measurement, I'm confident we can do much better. We've got a 70 femtofarad delta there. So we can further improve that by optimizing the current input. And I'm sure we get down to maybe a 10 femtofarad, even 1 femtofarad if you do enough averaging. Let's do that quickly. How are we doing for time? Almost there. One thing, actually, no, I think we'll leave it there now. Then I will go to the plotter. And I wanted to show you how we can do. So let's increase the test signal again and the auxiliary. And I want to show you about different frequencies. So not everybody wants to work at 1 megahertz. And I want to show you the effect that we can see there. Okay, so this is now at 1 megahertz, and we saw that it was you could measure within, for example, 10 microseconds. Let's now simply change this to 80 kilohertz. Of course, we might see a slight change there. Okay, and now let's just measure the. Okay, so we're seeing slightly different behavior. The bandwidth is probably a little bit too fast here. So what we can do is we can reduce that. It's currently at 100 kilo. Let's go to 10 kilo, for example, and that's nicely tidied things up. So that's always a trade-off between measurement speed and precision. So now if we stop there, let's have a look at a transient. Oh, we definitely have some resonance, some little bit of noise there. So let's indeed go down to maybe 5K. If your filter bandwidth is too open, it lets through the omega components, and that's what you're seeing there. So now we're filtering with 5 kilohertz, and that looks a lot better. Let's now bring in a couple of vertical cursors, and you can see here the time between these vertical cursors is, what is it? It's something like 80 microseconds. So it scales. The lower frequency, the longer you're going to have to wait for the instrument to return a reliable measurement, but nonetheless still very fast. And with that, I will draw the tutorial to a close, and I'm looking forward to your questions.